10.4 Torque. The outline of this video is as follows. We will explore the concept of torque, which is the rotational equivalent of force, and the cause of changes in rotational motion. First, we will formally define torque and learn the fundamental equation for calculating it. Next, we will introduce a related and very useful geometric tool called the moment arm, which provides a powerful alternative way to determine the magnitude of a torque. After that, we will establish the sign convention for clockwise and counterclockwise torques, and see how to calculate the net torque when multiple forces are acting on an object. Finally, we will apply all these concepts to solve a practical example involving the net torque on a cylinder. We are now ready to explore the cause of changes in rotational motion, which is a concept called torque. To understand this, let us first recall what we know about linear motion. A net force is what causes an object to accelerate. For rotation, there is an analogous quantity that causes an object to gain angular acceleration. This quantity is called torque, and you can think of it as the rotational equivalent of a force. However, torque depends on more than just the strength of a push or pull. It also critically depends on where that force is applied. For example, think about opening a heavy door. If you push right next to the hinges, it is very difficult to get the door to swing. But if you apply that same push far from the hinges, out by the doorknob, the door rotates much more easily. The force you applied is the same in both cases, but its effectiveness in causing rotation is completely different. This demonstrates the key idea. Torque depends on both the magnitude of the applied force and its distance from the axis of rotation. To understand what causes an object to change its rotation, we introduce a quantity called torque. Torque, represented by the Greek letter tau, is the measure of a force's ability to cause an object to rotate around a chosen axis. It is essentially the rotational equivalent of a force. The magnitude of the torque is calculated using the equation tau equals r times F times the sine of phi. In this expression, F is the magnitude of the applied force, and letter r is the distance from the axis of rotation to the point where the force is applied. The term phi represents the angle between the position vector, r, and the force vector, F. We can look at this equation in another way by defining a special term called the moment arm, denoted by d. The moment arm is equal to r times the sine of phi, and it represents the perpendicular distance from the axis to the line along which the force acts. This allows us to write a simpler, equivalent expression for the torque magnitude. Tau equals the force, F multiplied by the moment, arm d. So, the effectiveness of a force in causing rotation depends on the force's magnitude, its point of application, and its direction. To understand why torque depends on the angle of the applied force, it is helpful to break the force vector into components relative to the wrench. Let us resolve the force F into two parts, one parallel to the wrench and one perpendicular to it. The component parallel to the wrench has a magnitude of F times the cosine of phi. Notice that its line of action passes directly through the axis of rotation. Pushing or pulling along the length of the wrench will not cause it to turn, so this parallel component produces zero torque. The other component, which is perpendicular to the wrench, has a magnitude of F times the sine of phi. This is the part of the force that is effective at causing the wrench to rotate. This is why pulling at a 90-degree angle is most effective, because then the entire force is perpendicular. The key insight is that only the component of the force perpendicular to the lever arm contributes to the torque. This slide covers the practical strategies for getting the most effective turning action from a given applied force. First, to maximize torque, you should increase the distance from the axis of rotation to the point where you apply the force. This is why using a longer wrench or putting a pipe over a wrench handle makes it easier to loosen a stubborn bolt. Second, you should apply the force as close to perpendicular to the lever arm as possible. An angle of 90 degrees maximizes the moment arm and thus the torque. For instance, pushing sideways on a doorknob parallel to the door's face, results in zero torque and will not cause any rotation. The standard unit for torque is the Newton meter. A crucial point of caution: do not confuse torque with work. They happen to share the same units, but they are very different physical concepts. To summarize, the greatest torque is achieved by applying a force far from the pivot and perpendicular to the lever arm. Let us focus on a critical point that can be a common source of confusion. The torque produced by a force is not an absolute quantity with a single, fixed value. Instead, torque is a measure of how effectively a force causes rotation about a specific, chosen axis. The definition of torque involves the moment arm, which is the perpendicular distance from that axis to the line of action of the force. Because this distance is a key part of the calculation, changing the location of the axis will change the moment arm. This means that the very same force can produce different torque values depending on which axis of rotation you choose for your analysis. Therefore, whenever you calculate a torque, the first and most important step is to clearly define the axis you are measuring it with respect to. Often, more than one force acts on a rotating object, and each force can create its own torque. To find the overall effect, we calculate the net torque, which is the sum of all individual torques. To perform this sum correctly, we must pay close attention to the direction of rotation each torque would cause. By convention, we define a torque that produces counterclockwise rotation as positive. Conversely, a torque that produces clockwise rotation is defined as negative. This is an essential rule to remember. For the system shown in the previous figure, the force F1 creates a positive, counterclockwise torque. A force F2 creates a negative, clockwise torque. The net torque is the algebraic sum of these two. So, the total torque is the positive quantity F1 times D1 minus the quantity F2 times D2. In short, the net torque is the algebraic sum of all torques, and it tells us the object's overall tendency to change its rotation. Let us apply our understanding of torque to a concrete example. This problem involves calculating the net torque on a compound cylinder, which is a cylinder with two different radii, to see how competing forces affect its rotation. Imagine a single object shaped like a large drum with a smaller core section attached, similar to a large spool of thread. Both parts are fixed together and are free to rotate around a central axis. A rope is wrapped around the larger, outer drum, which has a radius r1. This rope pulls horizontally to the right with a force T1. At the same time, a second rope is wrapped around the smaller, inner core, which has radius r2. This rope pulls vertically downward with a force T2. Our goal is to find the combined rotational effect of these two separate forces. By calculating the torque produced by each force and then adding them together, we can determine the net torque on the cylinder. Let us calculate the net torque on the cylinder by analyzing each force individually and then summing their effects. This is a fundamental step in solving any rotational motion problem. First, consider the force T1, which acts at the larger radius r1. This force pulls the rope to the right, which would tend to rotate the cylinder in a clockwise direction. By convention, clockwise torques are negative. Since the moment arm is r1, the torque from this force, which we call tau1, is equal to negative r1 times t1. Next, we examine the force T2, applied at the smaller radius r2. This force pulls downward, which would cause a counterclockwise rotation. Counterclockwise torques are considered positive. The moment arm is r2, so the torque, tau2, is equal to positive r2 times t2. The net torque is the algebraic sum of these individual torques. Using the Greek letter sigma for sum, the net torque is tau1 plus tau2. Therefore, the final expression for the net torque on the cylinder is R2 times T2 minus R1 times T1. Now, let us substitute the given numerical values into our equation for the net torque. This will allow us to find not only its magnitude, but also the direction the cylinder will start to rotate. We start with our expression. The net torque equals R2 times T2 minus R1 times T1. The torque from the second force is 0.50 meters times 15 newtons, which equals 7.5 newton meters. This torque is positive because it tends to cause a counterclockwise rotation. The torque from the first force is 1.0 meters times 5.0 newtons, which is 5.0 newton meters. This torque is negative because it causes a clockwise rotation. Subtracting the second value from the first gives a final net torque of positive 2.5 newton meters. Since the final sign of the net torque is positive, the cylinder will accelerate and begin to rotate in the counterclockwise direction. Let us summarize the key ideas about torque. Torque is the rotational equivalent of force. It is the quantity that causes an object to have an angular acceleration, changing its state of rotational motions. We calculate the magnitude of torque, represented by the Greek letter tau, with the equation tau equals R times F times the sine of phi. In this formula, letter R is the distance from the axis of rotation to the point where the force F is applied, and phi is the angle between the force and the lever arm. An equivalent and often simpler way to write this is tau equals F times d, where d is called the moment arm. When multiple torques act on an object, we are interested in the net torque, which is simply the sum of all individual torques. By convention, we define torques that cause a counterclockwise rotation as positive, and those that cause a clockwise rotation as negative. Finally, a crucial point to remember is that the value of letter torque is always defined relative to a specific axis of rotation. Let us check our understanding of torque with two review questions. First, to loosen a stubborn screw, is it better to use a screwdriver with a longer handle or a fatter handle? The answer is a fatter handle. This is because a fatter handle increases the radius at which your hand applies the turning force. Since torque is the product of this radius and the force, a larger radius creates a greater torque for the same amount of effort. The length of the screwdriver's shaft has no effect on the torque applied to the screw. Second, imagine two equal forces applied to a wheel. One pushes horizontally at the very top, and the other pushes vertically downward at the rightmost point. Which force produces a larger torque? In this situation, both forces produce torques of the same magnitude. For both, the distance from the center is the wheel's radius letter R, and the force is applied perpendicular to that radius. Because both the force and the moment arm are identical, the resulting torques are equal.